Understanding how complex systems process information has long been a holy grail in fields ranging from neuroscience to physiology. We have tools like transfer entropy and mutual information, but they all share a fundamental blind spot. They collapse rich, multi-dimensional information dynamics into single scalar numbers. You lose the distinction between information that is redundantly shared, uniquely carried by one variable, or synergistically integrated across multiple variables. To fix this, researchers introduced Integrated Information Decomposition, or Ph-ID. Ph-ID breaks down the total information flow between a system's present and future state into 16 non-overlapping components. It's a complete taxonomy. But here's the catch. Every existing method to compute Ph-ID is mathematically locked to either discrete variables or Gaussian distributions. Real-world systems don't care about those assumptions. They're continuous, non-Gaussian, and highly structured. Until now, there was no general-purpose estimator to recover those 16 atoms from continuous data. That's where DIPHINE comes in. The diffusion-based Ph-ID Neural Estimator is the first method capable of estimating all 16 Ph-ID atoms from continuous, non-Gaussian systems without distributional assumptions. And it does it using a single, amortized score-based diffusion network. Today, we're going to break down exactly how it works, why the math behind it is surprisingly elegant, and what it reveals about real physiological systems. Let's start with the foundation. Ph-ID builds on partial information decomposition, or PID. In PID, you take multiple source variables and ask how much information they convey about a target. That joint mutual information gets split into 4 atoms: redundancy, unique information from each source, and synergy. Redundancy is information available from either source alone. Unique information is exclusive to one source. Synergy is information that only emerges when you look at the sources jointly. These 4 atoms form a lattice structure, and you recover the individual atoms by applying Möbius inversion to a cumulative redundancy function. It's essentially a deconvolution process that removes nested overlaps. Ph-ID extends this to time. Instead of one target, you have a future state. You now have a source lattice and a target lattice. Their Cartesian product gives you a double redundancy lattice with 16 elements. Each element, or atom, describes a specific mode of information flow. For example, information that is redundantly available in the present, but can only be decoded by observing both future variables jointly. To compute them, you need 9 distinct mutual information terms between subsets of the present and subsets of the future. Then you plug those 9 MIs into the double redundancy function and apply Möbius inversion across the 16 nodes. The bottleneck has always been estimating those 9 MIs in continuous, non-Gaussian settings. Traditional methods like KSG degrade with dimensionality. Variational bounds like MINE or InfoNCE require exponentially large datasets for tight estimates, and they saturate. Even if you train 9 separate models, you're ignoring shared structure and blowing up computational cost. DIPHINE sidesteps this by leveraging score-based diffusion models. The core idea relies on a result from score matching. If you can estimate the score function, which is just the gradient of the log density, you can compute KL divergences without ever explicitly modeling the density itself. Specifically, the KL divergence between 2 distributions can be expressed as an integral over a diffusion path of the squared difference between their score functions. Mutual information is just a KL divergence between the joint distribution and the product of marginals. DIPHINE exploits the identity that MI equals the expected KL divergence between a conditional distribution and its marginal. This means you only need to learn 2 score functions per MI term, one for the conditional density and one for the marginal. Here is where the amortization trick shines. Instead of training 9 separate networks, DIPHINE trains a single score network. It takes a concatenated state vector, applies a masking scheme, and learns all required scores simultaneously. The mask uses 3 states. A 1 means that block is diffused and its score is being learned. A 0 means it's held as clean conditioning data, and a -1 means it's marginalized out. By cycling through 12 unique mask configurations, the network approximates every conditional and marginal score needed for the 9 MI terms. At inference, you approximate the time integral via Monte Carlo, sampling over a handful of diffusion steps. It's computationally tight, and it shares representations across all terms. Once you have the 9 estimated MIs, you compute the double redundancy function by taking the minimum MI across candidate subcollections for each lattice node, then run Möbius inversion. But estimating MIs introduces error, and error compounds when you invert a lattice. This is where DIPHINE's theoretical contribution becomes critical. The authors prove that under reasonable assumptions, the mapping from the 9 MI estimates to the 16 atoms is locally affine. They derive the Jacobian of this mapping and show it factorizes into a Kronecker product of the source and target Möbius inversion matrices, multiplied by a selection matrix. Crucially, every entry in this Jacobian is strictly integer-valued, taking values in 0, +1, or -1. This integer structure gives you a clean way to bound error amplification. You can count exactly how many MI estimation errors contribute to each atom. The math proves that the red-to-red atom is always the most stable, receiving error from only one Mi term. The synergy-to-synergy atom, however, accumulates error from 4 to 6 different MI terms, depending on the underlying ordering of the mutual informations. Synergy to synergy is provably the hardest atom to estimate. This isn't just a heuristic observation, it's a structural property of the Möbius inversion on this lattice. The experimental validation confirms the theory. On Gaussian var.1 systems, where you can compute exact ground truth analytically, DIPHINE recovers the 9 MIs with mean absolute error around 0.01 to 0.02. The atom-level MAE scales exactly as predicted. Red to red stays near 0.001, while synergy to synergy sits between 0.018 and 0.036. When they scale to higher dimensions, with state vectors up to 20 dimensions, DIPHINE maintains its advantage. Baselines like KSG collapse entirely past 3 dimensions. Variational estimators like mine and InfoNCE stay competitive on raw MAE at low dimensions, but their atom MAE consistently lags behind. At 10 dimensions, DIPHINE pulls ahead decisively on atom recovery. The shared score representation prevents the independent variance that plagues separately trained estimators. To test it on real, non-Gaussian data, the authors applied DIPHINE to the Fantasia database, which contains continuous cardio-respiratory recordings from young and elderly healthy subjects. They extract the RR interval and respiration signals, treat them as a bivariate system, and compute the full Φ-ID decomposition. The results map directly to known physiology. Transfer entropy is higher in young subjects, dominated by the respiration to heart rate direction. In elderly subjects, both directions weaken and the asymmetry attenuates, matching the known decline in parasympathetic coupling with aging. More interestingly, the Φ-ID decomposition shows that this transfer is primarily driven by the synergy to redundancy atom. Information is synergistically integrated in the source, but redundantly available in the target. As subjects age, the self-storage atoms increase, suggesting a decoupling of the subsystems. Each variable's future becomes more predictable from its own past alone, as cross-variable coupling weakens. DIPHINE isn't a magic bullet. It's currently restricted to ergodic systems, bivariate partitions, and relies on the MMI redundancy function, which can occasionally yield negative atoms. Extending it to non-ergodic systems, or n greater than 2 partitions, would require navigating lattices with superexponential growth. The computational cost of training diffusion-based score networks is also non-trivial, though the amortization strategy significantly mitigates it compared to training independent estimators. Still, the impact is clear. DIPHINE removes the Gaussian and discrete bottlenecks that have constrained information decomposition for years. It gives us a unified, theoretically grounded, and empirically robust way to map the fine-grained architecture of information flow in continuous systems. For anyone working in complex systems, neuroscience, or information-theoretic machine learning, this is a foundational step toward measuring how real systems actually compute, store, and transfer information. If you're interested in the full mathematical derivations, the masking scheme implementation details, or the complete atom matrices from the physiological analysis, the paper and code are available. I'll leave links in the description. Thanks for watching, and keep pushing the boundaries of how we measure information.